That is one model in 2 runtimes on one laptop. 12.66 tokens a second against 8.52. 49% in favor of MLX on a machine sitting on my desk. If this were most videos about local AI, that number would be the whole video. It is going to turn out to be the least interesting thing I measured, and by the end of this, you will know why I do not trust it, including the version of it I just showed you. Quick note before we dig in. If you find this useful, subscribe and drop a topic you want explained in the comments. Now let us get into it. Here is what is actually on the machine. The model is Q23.627b, and Ollama ships it in 2 builds. One is compiled for MLX, which is Apple's own array framework, written for the unified memory architecture on Apple Silicon. The other is GGUF, the format llama.cpp uses, which runs more or less everywhere. Same weights, same parameter count, same quantization target. The only variable is the runtime underneath. The machine is an M2 Max with 32 gigabytes of unified memory. That matters more than it sounds like it does, because a 20 gigabyte model on a 32 gigabyte machine is not comfortable. There is room, but there is not much room. Before any numbers, the method, because the method is where most benchmarks quietly go wrong. 2 things there are worth saying out loud. The first is that the timing comes from ollama's own counters, not from a stopwatch around the call. That matters because a stopwatch includes the model loading, and loading a 19 gigabyte file takes longer than the writing does. Fold those together and a fast runtime looks slow for a reason that has nothing to do with the runtime. So load time is measured, reported, and kept separate. The second is that every figure is a median of timed runs, not the best one. That sounds like a small choice. Hold on to it, because it is about to become the entire story. This is the script that produced the file you saw. It is not pseudocode and it is not a sketch. 3 prompts, 3 timed runs each. Both models warmed first, so nobody pays the cold start twice. Then it stops each model to hand the memory back before the next one loads. So, the headline result. MLX takes it. 12.66 tokens a second against 8.52 on the median, which is at 49%. It also holds 19 gigabytes resident against 20, and it cold loads in 7.2 seconds against 11.8. 3 measurements all pointing the same way. Faster, smaller, quicker to start. That is where I could have stopped. It is a clean result. It agrees with what everybody says about MLX on Apple Silicon, and it is exactly the kind of tidy number that gets repeated. So let us look at the 3 prompts separately instead of at the median across them. On the first prompt, MLX is 71% faster. On the second, 49. On the third, 11. Same 2 models, same machine, same session, minutes apart. Every one of those runs generated exactly 300 tokens because they all hit the same cap, so this is not a case of one test simply being longer than another. The advantage is real, and it is somewhere between enormous and negligible depending on what you happen to ask. An average of 71 and 11 is not a description of anything. It is a number that exists, and it tells you almost nothing about what will happen the next time you press enter. Now, when you see a spread like that, the temptation is to explain it, and I had an explanation immediately. The 3 prompts were different lengths. The shortest prompt gave the biggest lead, the longest prompt gave the smallest, and the middle one landed in the middle. Prompt length goes up, MLX advantage goes down. It is monotonic across all 3. It has an obvious mechanism, and it would have made a very satisfying paragraph. It is also 3 data points. 3 points will line up in whatever order you like often enough that lining up means nothing on its own. So instead of writing that paragraph, I wrote a second script to try to break it. This one pins the output length and moves only the prompt from about 40 tokens up to about 1200 using the same filler sentence repeated so nothing else changes. If the prompt length theory is right, the MLX lead should fall as you go down that table. Here is what came back. 10%, 18%, -14%, 37%. It does not fall. It does not do anything with the shape. And in the third row at 441 prompt tokens, GGUF is simply faster. The runtime that lost every headline comparison wins that one outright. My explanation was wrong. Not incomplete, not approximately right, wrong, and the test that killed it took about 4 minutes to run. I want to be careful about what I claim here, because there is a confound sitting in plain sight. These runs happened back to back on a laptop, and a laptop under sustained load gets hot and slows itself down to cope. That poor 141 token row might be telling you something about MLX. It might just be telling you that the machine was warm. I did not control for thermal state, so I cannot separate those two, and I am not going to pretend otherwise. But notice that the confound does not rescue the original number. If thermal drift can move a result by 50 percentage points, then the tidy 49% from the beginning was also measured on a machine at some particular temperature in some particular state, and it is subject to exactly the same doubt. There is one more thing in the raw data that says the same thing more quietly. On a single prompt, MLX produced 15.6, then 12.41 tokens a second. Same prompt, same model, minutes apart, a 25% swing. GGUF, on that same prompt, ran 7.84 to 8.67. It is slower, and it is boring, and boring is a feature. If you are sizing a machine or promising someone a response time, the runtime that is predictably slower is easier to build on than the one that is sometimes much faster. So here is the honest conclusion, which is not the one I expected to write. On this machine, MLX is faster on the median. It holds a gigabyte less memory, and it starts up in about half the time. Those three things are consistent across everything I ran, and I would act on them. But the size of the speed advantage is not a fact about MLX. It moved between +71 and -14% across my own tests in one afternoon on one machine, and I cannot fully explain why. Which means the useful takeaway is not a number at all. It is that anybody quoting you a single tokens per second figure for this comparison, a blog post, a benchmark table, a video, this video, is quoting you one sample from a distribution they probably did not look at. The number is not fake. It is just much narrower than it sounds. If you want to know what these runtimes do on your hardware, the only reliable way is to measure it there, and that is about 10 minutes of work. Pull both builds, run the two scripts, and read your own table. Everything in this episode is in the repository linked below, including the raw JSON with every individual run, not just the medians, so you can check my arithmetic and disagree with my reading of it. And if your numbers come out different from mine, that is not a problem with either of us. That is the actual finding. That is the core of it. If this helped, hit like and subscribe, ring the bell for the next deep dive, and tell me in the comments what you want broken down next. Thanks for watching.